All right, let's break down the magic of solar panels. We're going to unpack this simple, cool process I call the silicon sandwich. Basically, how we turn a simple sunbeam into actual usable electricity. I mean, just think about it for a second. Most of us are paying a power bill every single month, right? But we're literally surrounded by this incredible amount of free, untapped energy. Let's kick things off with a fact that might just blow your mind. Get this. The sun blasts the Earth with 10,000 times more power than the entire world actually needs. That is just a staggering amount of potential. So today, we're going to learn exactly how this technology catches a tiny little piece of all that power. Okay, so let's get right into it. At the absolute heart of every single solar panel is what I call the silicon sandwich. We're going to look at its core ingredients, and more importantly, the incredible electric tension that they create. So the panel itself, it's mostly made of silicon, and yet that's the same basic stuff you find in sand. But, and this is a big but, this isn't just any old silicon. It's been specially engineered into two totally different opposing layers, and that's the key to this whole process. Here is where the real magic starts. You've got these two opposing layers, and they create this fundamental conflict. The first one, the N-type layer, is like a super crowded room. It's just packed with way too many electrons. Then you have the P-type layer, which is like a room with a bunch of empty seats. It's full of these holes just waiting for electrons to come fill them. What you get is this incredible amount of stored potential energy. You could think of it like a microscopic tug of war. You have all these electrons in the crowded room, and they are desperate to jump over and grab one of those empty seats. The whole system is just buzzing with tension, waiting for something to kick it all off. Okay, so we've got the tension built up, but how do we unleash all that stored power, right? Well, it all comes down to one tiny, tiny particle of light coming all the way from the sun. You know, sunlight isn't just warmth or brightness, it's an actual physical stream of countless tiny energy packets. They're called photons. These things are constantly traveling from the sun and just bombarding the Earth. So this is the key moment, the absolute trigger for the whole thing. What happens when one of those tiny particles of light physically slams into the solar cell right at that point where all that tension exists between the N-type and P-type layers? Well, it's this beautiful three-step chain reaction. Step 1, a photon strikes the silicon with enough force to hit an electron. Bam! Step 2, that impact knocks the electron completely loose from its atom. Step 3, the panel's built-in electric field, that tension we were just talking about, it takes that freed electron and shoves it forward. Here's a great way to think about it. It's like a game of pool. The photon is the cue ball. It comes in, strikes the electron, the one ball, perfectly, and just blasts it into motion. It's this high-speed atomic-level collision happening over and over and over again. Here's the crucial part. This process isn't random at all. The internal structure of that solar cell creates a one-way street for these electrons. Once one gets knocked loose, it can only move forward, out of the cell and into the wires. That directed flow of electrons, well, that's literally the definition of an electrical current. That tiny little current from just one electron, that's the very beginning of all solar power. But how do we scale that up? How do we go from a microscopic trickle to a flood of energy powerful enough to run your entire house? Well, let's take a look. Okay, check this out. A single solar cell all by itself produces only about half a volt of electricity. That is incredibly weak. I mean, we're talking nowhere near enough to even charge your phone, let alone power anything significant. To get any useful power, manufacturers have to wire dozens of these cells together in a series to build up the voltage. That's what makes a solar panel. Then you take multiple panels and wire those together into an even larger system called an array. It's this massive grid of cells all working together in unison that generates the power you actually need for your home. Now, this technology is absolutely amazing, for sure, but it's not perfect. For the full picture, we got to do a little reality check and talk about its current limitations, especially when it comes to efficiency. Here's the deal. Most commercial solar panels you can buy today only capture and convert about 20% of the sun's energy that actually hits them. Where does the other 80% go? Well, it's mostly just lost as heat. That's because silicon can only absorb certain wavelengths of light. The rest of the sunlight either passes right through or just heats up the panel. Improving this number, that's one of the biggest goals in solar research right now. Okay, so now that you get the nuts and bolts of how it works and its limitations, let's bring this all back to you. We've put together a quick little checklist to help you figure out if your own home might be a good candidate for solar. Really, there are three critical questions you need to ask yourself. Number one, roof direction. Does your roof face the sun for most of the day? For most people, that means south-facing. Number two, local sun hours. How many sunny days does your area actually get every year? The more, the better, obviously. Number three, battery storage. Are you going to need power at night or on cloudy days? If the answer is yes, then you're going to need a battery system. Feel free to go ahead and screenshot this. Now, as this tech gets more and more efficient, the answers to these questions get a lot easier for pretty much everyone. Which leaves us with one final thought. How far away are we, really, from a future where every single roof is its own power station?